in Sydney, Australia. His vita and his scientific work are so remarkable that I asked my colleague, Professor Harde, to introduce Professor Murray.
Today we are very happy to have here you, Professor Salby, as a highly recognized guest from far abroad. He is known all over the world as one of the few specialists who really have a view over the whole area of the climate development. Despite of his long relationship to the most renowned climate institutes, he has preserved his own critical and constructive reasoning, which in some parts is in real contradiction to the official expert opinion and also faces the assessment of the IPCC. It's our great pleasure, therefore, to welcome you here today at our university, and this although you have a right tight schedule on your European tour. In his talk today, you will present the most actual discussion of climate, to my opinion, with the title Relationship between Greenhouse Gases and Global Temperature. It's your time. Thanks.
Thank you, Professor Harde and Professor Glauer, for those kind words. And thanks also to Professor Wernholt for arranging this visit. Those of you outside of physical science will not be familiar with some of this development, which is technical. Relax. You will grasp the important consequences, which will be self-evident. I came to this topic by way of accident. Well, sort of. After relocating to Australia, I found myself waiting for resources. Eventually, I undertook the production of a new book. A book never proceeds as quickly as one would like, because when it comes to putting pen to paper, one finds that the understanding of key issues is inadequate. On the subject of climate, one of the most conspicuous is ironically the most central. The recent interpretation of climate revolves about changes of atmospheric composition. It rests on three pillars. One, proxy evidence of past atmospheric composition. Two, modern changes, those actually observed. And three, simulations of their impact by climate models. For past changes, observations do not exist. We have only proxy evidence from ice cores. The proxy record relies on air bubbles that become embedded in ice as it sinks under the weight of the overlying column. In green is the record of proxy CO2. It changes by 100 ppmv, parts per million by volume, on the timescale of 100,000 years, with smaller changes on shorter timescales. In mauve is the record of proxy methane. It too changes, mirroring changes of CO2. In blue is proxy temperature, inferred from isotopic oxygen. It changes in similar fashion, undergoing swings of 8 Kelvin during the glaciation cycle. Temperature that's anomalously cold coincides with ice ages, accompanied by CO2 and methane that are anomalously low. Temperature that's anomalously warm is accompanied by just the reverse. These ancient changes of composition are the linchpin of modern interpretations. They are the reference against which changes during the 20th century, those actually observed, appear unprecedented. Their importance is recognized by the IPCC, the Intergovernmental Panel on Climate Change. The mechanistic explanation of these CO2 variations remains one of the major unsolved questions in climate research. The coherence, that is the codependence between atmospheric composition and temperature, is dominated by the cyclic swing over 100,000 years. But their coherence is not unique to the glaciation cycle. Filtering the records of CO2 and temperature to periods shorter than 50,000 years removes the glaciation cycle. What remains is broadband variability. CO2 evolves coherently with temperature over a wide range of timescales. Their coherence in the proxy record is universal. Plotted here is the cross-correlation between temperature and CO2 as a function of lag. The cross-correlation measures their interdependence. It exceeds 0.8. Changes of temperature in CO2 are strongly interdependent. If one changes, so must the other. Nearly symmetric, the cross-correlation decreases with lag, slower for positive lag, where changes of CO2 follow changes of temperature. In fact, the correlation maximizes at small positive lag, less than 1,000 years. This is their coherence spectrum as a function of frequency. It measures the interdependence of CO2 and temperature on different time scales. The shading marks the levels of significance. So anywhere above the shading is strongly significant. That is, it's real and unlikely to be an artifact of the numerics or the sampling. CO2 and temperature evolve coherently on all timescales longer than 10,000 years. In dotted is their phase spectrum. It describes the relative timing between changes of CO2 and changes of temperature. Phase hovers near zero. Temperature and CO2 evolve coherently and nearly in phase. These changes refer to proxy CO2 in ice, not atmospheric CO2 actually observed. We need to understand how the two are related. This is the observed record in actual measurements of atmospheric CO2 and temperature. It extends back half a century. Plotted here is their cross-correlation. It exceeds 0.5 at positive lags, where changes of CO2 follow changes of temperature. Hence, observed temperature and CO2 are also strongly interdependent. Their correlation maximizes near a lag of 10 months, but it's significant across a wide range of positive lag. The asymmetry indicates that observed CO2 evolves coherently with temperature, but lags across a wide range of timescales. CO2 is produced and destroyed at the Earth's surface, but in the atmosphere, it's conserved. Its rate of change in CO2 mixing ratio, R, must therefore equal net emission from the Earth's surface. The left-hand side of this equation is the time derivative of CO2, the rate of increase of CO2. This equation says that the rate at which CO2 increases is equal to the rate that is emitted by all processes that produce it at the Earth's surface. In green is net emission of CO2, collectively from all sources and sinks, human as well as native sources. Unlike human emission, native sources and sinks are inherently sensitive to surface conditions. Field measurements reveal that native emission of CO2 depends strongly on temperature. In blue is global surface temperature. Net CO2 emission tracks the history of surface temperature, achieving a correlation of 0.63. Notice the correspondence holds even for systematic changes during the last half century, when net emission intensified by 100%, from 1 ppmv per year to 2 ppmv per year. The observed relationship means that to leading order, the rate of change of anomalous CO2, the departure from its mean, is proportional to anomalous temperature, where gamma is the sensitivity to temperature of CO2 emission. CO2 must therefore evolve like the integral of temperature. The integral of temperature means the cumulative temperature. Temperature in one year, which is proportional to the emission of CO2 that year, plus the temperature of the next year, which is proportional to the CO2 emitted that year, and so forth. That is the integral temperature. And it must then be proportional to the cumulative net emission of CO2 from all sources and sinks, human and native. Observed CO2 and temperature then evolve coherently, as in the proxy record, but now they evolve in quadrature. If temperature evolves like cosine of time, CO2 must evolve like the sine of time, undergoing the same variation, but lagging temperature by a quarter cycle. More generally, the evolutions of CO2 and temperature can be expressed through Fourier integral as a synthesis of such spectral components. For each frequency omega, the complex amplitude of mixing ratio, R of omega, lags the complex amplitude of temperature, T of omega, by 90 degrees or a quarter cycle. As different spectral components in these integrals have different periods, no single lag will simultaneously align all components. Covariance between CO2 and temperature must therefore be distributed widely over positive lag, as was observed. This is their coherent spectrum, likewise from the observed record. Temperature and CO2 evolve coherently on all timescales longer than a couple of years. In dotted is the phase between temperature and CO2. It hovers near minus 90 degrees. In the observed record, they also evolve coherently, but in quadrature. At each frequency, CO2 lags temperature by a quarter cycle. CO2 and temperature evolve coherently in both the proxy record and the observed record, but their relationship differs fundamentally. To connect the two, we must consider the evolution of CO2 in ice. It has two contributions. One, the composition of air when it resided at the top of the ice column, inside the firn, where snow is porous enough to assume atmospheric mixing ratio, Ra. This sets the initial mixing ratio, which subsequently descends. Two, non-conservative influences, which damp anomalous composition as it descends, involving irreversibility. Those influences modify mixing ratio from the initial value imprinted in the firn, yielding the mixing ratio in ice, Ri. Having similar impact is measurement error associated with the extraction and analysis of ice. We consider changes of composition under the observed relationship to temperature, but in a general framework that accounts for non-conservative influences, which modify composition on timescales longer than in the observed record. The conservation equation governing mixing ratio is forced by the temperature-induced source. That's what's represented in the correlation between CO2 emission and temperature. If you change temperature, you change CO2 emission rate. And so that appears on the right-hand side of the equation, which essentially drives the rate of increase of atmospheric CO2. But the conservation equation is then also forced by a non-conservative sink, which intensifies with anomalous mixing ratio, R. Embodied in the damping rate, alpha, is the time scale of non-conservative influences, whether they destroy anomalous CO2 over a year, a century, or a millennium. The non-conservative sink represents removal mechanisms that intensify with concentration. Such mechanisms also exist in the atmosphere before air becomes embedded in ice. Their dependence on mixing ratio is illustrated by biomass. Increased CO2 results in a proportionate increase of vegetation. That must be attended by a proportionate increase of CO2 removal. Analogous considerations apply to marine biota, which play a similar role. All right, now I want you to take a deep breath. Are you ready? Here we go. Multiplying the conservation equation by temperature and taking the expectation yields a balance governing the cross-covariance between CO2 and temperature. The cross-covariance is just their cross-correlation, unnormalized. It's forced by the autocovariance of temperature, which characterizes the time scale of temperature variations. Temperature is represented stochastically as a first-order Markov process. Its autocovariance then decays exponentially with lag tau. This system can be solved in closed form. It yields the cross-covariance between CO2 and temperature, the diagnostic evaluated earlier from the proxy and observed records. The cross-covariance, in turn, determines the cross-spectrum, which is just its Fourier transform. Represented in the cross-spectrum are the coherence and phase, the other diagnostics evaluated from the proxy and observed records. A closed-form solution has a feature that is unrivaled. You can see exactly what's going on. The solution assumes two limiting forms. For timescales much longer than the damping time, changes are slow. The conservation equation then reduces to a balance between the temperature-induced source and the non-conservative sink. CO2 growth rate is then limited because temperature-induced emission is offset by non-conservative absorption. In this limit, the phase between CO2 and temperature approaches zero. The two evolve in phase. These features characterize changes of composition that are strongly non-conservative. This means that CO2 is removed by dissipative processes almost as quickly as it's introduced by temperature-induced emission. The features are manifest in the proxy record, which involves timescales longer than several thousand years. This is the calculated cross-covariance between CO2 and temperature in the limit of long time scale. Look familiar? At the bottom is the cross-covariance evaluated earlier from the proxy record. At the other extreme are timescales much shorter than the damping time. Changes are then fast. The conservation equation then reduces to a balance between the growth rate of CO2, that's the time derivative on the left-hand side, and the temperature-induced source, which is then uncompensated. CO2 growth rate is therefore unlimited. CO2 can grow arbitrarily fast, depending on temperature. In this limit, the phase between CO2 and temperature approaches minus 90 degrees. The two evolve in quadrature. CO2 lagging temperature by a quarter cycle. These features characterize changes of composition that are conservative. Conservative means that CO2 removed by dissipative processes cannot keep up with its introduction by temperature-induced emission. The dissipative processes are slow. These features are manifest in the observed record, which involves timescales shorter than a century. This is the calculated cross-covariance in the limit of short time scale. At the bottom, the cross-covariance evaluated earlier from the observed record. The impact of non-conservative influences is reflected in the phase, which differs fundamentally in the proxy and observed records. At the top of the ice column, in the firn, ice mixing ratio, Ri, equals atmospheric mixing ratio, Ra. The signature of atmospheric composition, it then descends with speed c. Its evolution is described by the Lagrangian derivative. The rate of change in a reference frame descending with the ice. If non-conservative influences in ice are absent, the Lagrangian derivative vanishes. The atmospheric signature then descends conservatively, preserving changes imprinted in the firn. If non-conservative influences are present, the Lagrangian derivative is damped at rate alpha I. This is the conservation equation governing CO2 in ice. It's solved through the method of characteristics, wherein depth translates into time. How long for ice to have descended to a given level. The conservation equation then assumes the same form as the one just solved, but with effective damping, alpha E, which is the sum of damping in the atmosphere and subsequent damping in ice. Its solution determines the power spectrum of CO2 in ice. The change of proxy CO2 at one frequency versus at another frequency. As the solution holds for arbitrary damping, it can be evaluated for zero damping in ice. What would have been registered in ice under conservative conditions. That, in turn, represents the power spectrum of CO2 in the atmosphere. The quotient then describes, frequency by frequency, how changes of atmospheric CO2 relate to changes of proxy CO2, namely those seen in ice. The variance of atmospheric CO2 is magnified over that apparent in the proxy CO2. Equivalently, changes of atmospheric CO2 are underestimated in the proxy record. Their underestimation increases with time scale quadratically. What you're looking at is the ratio of the change in CO2 in the atmosphere versus the change that appears in ice as a function of frequency or inverse time scale. And so as you go to very large frequencies, that ratio goes to 1, which means that the change in the atmosphere equals the change we see in the ice. But as you go to low frequencies, longer time scales, that ratio quickly gets much larger than 1. And that means the change in the atmosphere is much greater than the change that's apparent in the ice. For this reason, even weak damping in ice can substantially reduce the change of mixing ratio apparent on long time scales. The effect is illustrated by damping that recovers the cross covariance in the proxy record, seen earlier. A change of proxy CO2 on a timescale of 10,000 years then underestimates the atmospheric change by a factor of 2. Swings of proxy CO2 of 20 ppmv then actually derive from changes in the atmosphere of 40 ppmv. A change of proxy CO2 on a timescale of 100,000 years then underestimates the atmospheric change by a factor of 15. Swings of proxy CO2 of 100 ppmv during the glaciation cycle then derive from changes in the atmosphere of order 1,000 ppmv. Observed changes during the 20th century are then hardly unprecedented. The non-conservative influences considered until now operate on different scales with equal efficiency. In ice, however, damping can vary with the vertical scale of proxy structure, which translates into time scale. Scale-selective damping is symbolized by diffusion, which varies inversely with vertical scale. Short scales with steep gradient are diffused faster than long scales with flat gradient. The conservation equation in ice then assumes a form similar to that seen earlier, but with the boundary value, CO2 in the firn, absorbed into the equation. The real addition is the second derivative, which represents diffusion. Transforming depth into time reduces the conservation equation to the diffusion equation. It can be solved through Fourier transform. The solution emerges as a spectrum of vertical wave numbers k, which descend non-dispersively with speed c. This integral is analogous to the Fourier integral you saw earlier. It represents the superposition of waves of different scales, which all descend with the speed of ice. If we can determine the amplitude and phase of individual wave numbers, then we have solved the conservation equation. That, in turn, tells us how CO2 evolves in ice. The kth wave number is governed by a conservation equation. It has the same form as the equation solved earlier. The effective damping now includes a contribution that increases quadratically with wave number. Since depth translates into time, wave number translates into frequency. High frequencies, short time scales, are damped more than low frequencies, long time scales. As before, the solution enables proxy CO2, namely the CO2 evident in ice, to be compared against atmospheric CO2, namely what was really in the atmosphere. Changes of atmospheric CO2 are again underestimated in the proxy record. But now, their underestimation increases with frequency. High frequencies, short timescales that are conservative are suppressed in ice. Leaving low frequencies, long timescales that are strongly non-conservative. Calculated first is the cross-covariance under non-diffusive conditions in ice. For damping and temperature variability seen earlier to recover the cross-covariance in the observed record. What's measured in the atmosphere? The covariance in ice between temperature and CO2 then has the same form as in the atmosphere. It decays on a timescale of only months. On the extended timescale of the proxy record, it therefore collapses into a spike, as narrow as can be represented at a resolution of 1,500 years. Introducing diffusion in ice transforms the cross-covariance into the upper curve. Describing much longer timescales, the calculated cross-covariance then recovers that evaluated from the proxy record.
Both curves follow from the same sensitivity to temperature of CO2 emission, that observed during the 20th century.
By removing short timescales, those resolved in the observed record, scale-selective damping discriminates to long timescales, which are strongly non-conservative. That's what's found in the proxy record. This behavior has two key implications. First, non-conservative influences inherent in the proxy record enable past atmospheric changes to be significantly underestimated. More importantly, the same physical mechanism which governs ancient changes, timescales longer than several thousand years, also governs modern changes, timescales shorter than a century. And that brings us to modern changes, those actually observed. The observed record of CO2 spans the last half-century. Extending it backward with the proxy record indicates a systematic increase since the 19th century. In red is delta 13, the relative concentration of the two isotopes, carbon-13 to carbon-12. It evidences a decline, mirroring the increase of CO2. Together, these proxy records comprise the smoking gun of human emission. Vegetation is slightly leaner in carbon-13 than the atmosphere. So is its ancestor, fossil fuel. Coal and oil each derive from ancient vegetation. Emission from combustion of fossil fuel therefore adds CO2 to the atmosphere, enriching its concentration there. That's the green curve. The CO2 added, however, is leaner in carbon-13 than the atmosphere, thereby diluting its concentration there. That's the red curve. The glove fits. In truth, however, it's but one finger. Combustion of fossil fuel is one of many sources of CO2. Others involve a wide range of native processes. Most are poorly documented. The recent interpretation is that opposite changes of CO2 and carbon-13, the green and the red curves, are the signature of human emission. For this interpretation to be valid, other sources of CO2, native sources, must have the same concentration of carbon-13 as the atmosphere, which would then be left unchanged. That is, CO2 emitted by native sources must not dilute carbon-13 in the atmosphere. The observed increase of CO2 and decrease of carbon-13 can then follow only from the human source. In reality, our knowledge of native sources is limited. The little we do know is that they are dynamic. Native sources depend intrinsically on environmental conditions, cloud, moisture, temperature, even on the prevailing ecosystem. Why should we care? This is the estimated contribution from all sources and sinks. The human source is of order 5 gigatons per year. By comparison, the ocean emits of order 90. Land emits another 60. Total emission from native sources is thus of order 150 gigatons per year. 96% of the total. It's approximately balanced by native sinks, which absorb about as much. The key word, approximately, because native sources and sinks are 2 orders of magnitude stronger. Even a minor imbalance can overshadow the human source. Moreover, if those sources involve carbon-13 leaner than in the atmosphere, as many do, all bets are off. In truth, only one component of the CO2 budget is known with any certainty: human emission, implicitly through records of extraction. How much coal and oil are dug up? It accounts for only 4% of the total. The other 96% from native sources remains obscure because global observations of surface flux, namely the rate at which CO2 is coming into the atmosphere, do not exist. We have continuous records from only a handful of sites, and even those are records of CO2, not its surface flux, which forces the atmospheric budget of CO2. This leaves the dominant sources and sinks, the big arrows, not sharp, but fuzzy. If they change, we haven't the observations to know, at least not directly. Fortunately, that's not the end of the story. What controls atmospheric CO2 is net emission, collected from all sources and sinks. Net emission is just the sum of the CO2 added by all sources, minus the sum of CO2 removed by all sinks. It determines the growth rate of global mean CO2. Because it's conserved in the atmosphere, CO2 is homogenized by the circulation, which mixes it and makes its distribution approximately uniform on long time scales. This is the global distribution of CO2, only recently available from satellites like Salby. Even these modern observations are limited to continents, but that's where the human source is. Large values in yellow and red are a signature of source regions. Notice, they're not found in the industrialized centers, the Ohio River Valley of the US, or Western Europe, or even China. Rather, they appear in the Amazon basin, tropical Africa, and Southeast Asia. Those regions have little human population, let alone industrialization. What I really want you to notice is that even in those source regions, CO2 deviates from its global mean by less than 5%. Local values of CO2 are therefore a good approximation to its global mean, which in turn provides the history of net global emission. In green is net emission during the satellite era, when we have global observations of temperature. It has an average of about 1.5 ppmv per year, but it varies between years dramatically, by over 100%, from nearly 0 in some years to almost 3 ppmv per year in others. Do I need to tell you that human emission doesn't do anything like this? In red, human emission increased smoothly. It mirrors the growth of human population, with deviations of only a couple of percent. By contrast, observed deviations of net emission exceed 100%. They are incoherent with human emission. Net global emission evolves independently of the human contribution. The record of net emission does, however, resemble surface properties. During 1991-92, net emission decreased by 70%. It gradually rebounded over the following 3 years. That event coincided with the eruption of Pinatubo, which decreased global temperature in the same fashion. During 1997-98, net emission increased by 200%. That event coincided with the El Nino then, which increased global temperature. The correspondence during these events is consistent with field measurements of CO2 emission. That is, local measurements where someone goes out, sticks a pipe in the ground, and actually measures what comes out of the surface or what comes out of the ocean. Those campaigns reveal strong sensitivity to surface properties. Temperature, seen earlier, supported over a continent by soil moisture. An increase in either induces increased emission of CO2 from native sources. The contribution from induced emission of CO2 follows by projecting the observed record of net emission, that's the green curve, onto contemporaneous records of temperature and soil moisture. In blue is the induced component of net emission, the part that operates coherently with surface properties. Although it accounts for only 2 key surface properties, the induced component closely tracks net emission. It achieves a correlation to the observed record of CO2 net emission of 0.93, accounting for nearly all of the history of net global emission. Most of the dependence comes from temperature alone, which achieves a correlation of 0.8. In red is observed emission of carbon-13. It has a mean that's negative, consistent with the decline of carbon-13 seen earlier. But like CO2, it varies dramatically by more than 100%. In blue is minus the induced component, the part that operates coherently with surface properties. Like CO2, it varies coherently with observed net emission of carbon-13. Just opposite. When temperature increases, emission of carbon-13 decreases, and vice versa. Likewise, when CO2 net emission increases, that's the green curve, carbon-13 net emission decreases. That's the red curve. Does this ring a bell? Remember the smoking gun? Opposite changes of CO2 and carbon-13 are the same ones apparent in the ice proxy. The latter is regarded as a signature of human emission. But in the satellite record, the changes are clearly not from human emission. Not unless you believe human emission causes volcanic eruptions and El Nino. In mauve is the observed record of methane emission. It suffers from the same limitations as the record of CO2, but it's even shorter. It's noteworthy that human sources of methane are independent of human sources of CO2, unless you believe combustion stimulates bovine flatulence, flatulence von Kuh. In blue is the induced component, the part that operates coherently with temperature and soil moisture. The same surface properties, which account for most of the history of net CO2 emission, also account for most of the history of net methane emission, achieving a correlation of 0.94. That's what you saw in the proxy record. To first approximation, the blue curve for CO2 emission is just temperature. It follows from the sensitivity of native emission, the part induced by changes of surface properties. Integrating that emission over time, that is, adding the induced emission during 1 year, plus the next year, and so forth, yields the cumulative CO2 introduced by surface properties. That represents the contribution to observed changes of CO2 from native sources, which depend on surface properties. In blue is the induced component of CO2. It's determined entirely by surface properties, temperature from the satellite MSU, and soil moisture from NSEP reanalyses. In green is the observed record of CO2. In blue is the induced component of methane. It too is determined entirely by temperature and soil moisture. Notice, after the early 90s, the trend in the induced component nearly vanishes. In mauve is the observed record of methane. The sensitivity of emission evaluated during the satellite era should in principle determine the induced component in earlier years. But before the satellite era, global observations are lacking. Most of that sensitivity, however, comes from temperature. Global temperature before the satellite era is estimated from the surface network of thermometers, albeit with only partial coverage of the Earth. In blue is the induced component of CO2, again derived from the satellite MSU, but now determined only from temperature. As before, it tracks the observed record of CO2 in green. In black is the same information, but now based on the surface network from CRU, the Climate Research Unit of the UK Met Office. The sampling uncertainty is shaded, representing the contribution from native sources. It too tracks observed CO2 during the satellite era. In fact, it tracks it throughout the instrumental era, back to 1960, when atmospheric observations began. Observed CO2, that's the green curve, and the induced component, that's the black curve. Then both approach 300 ppmv. Before 1960, the induced component continues to decrease, approaching 275 ppmv in 1880. The uncertainty, which increases backward, is then wide, ranging between 220 and 330 ppmv. During this early period, continuous observations of atmospheric CO2 are non-existent. We have only proxy CO2. In green is the ice proxy you saw at the start. It too decreases backward, approaching 290 ppmv in 1880. Let there be no ambiguity about what you're looking at. The black curve is just the integral of temperature, scaled by the observed sensitivity of CO2 emission.
And the sensitivity of emission has been evaluated only from large interannual swings of emission, changes that are clearly independent of human emission.
The modest discrepancy before 1940, about 10 ppmv, lies well within the sampling uncertainty of the surface network. But in light of the agreement during the instrumental era, the last half-century, it may actually reflect error in proxy CO2. It may also reflect limitations of the surface network. At the bottom is coverage of the Earth by surface thermometers. It maximizes near 1960 at 35%. That's how much of the Earth is land. Before 1960, coverage plummets. By 1880, coverage of the Earth by the surface network is less than 8%. The IPCC has proclaimed the following: all of the increase in CO2 since pre-industrial times is caused by human activity. The increased CO2 is known to be caused by human activity because the character of CO2 in the atmosphere, the ratio of its heavy to light carbon atoms, has changed in a way that can be attributed to addition of fossil fuel carbon. The observed sensitivity of native emission of CO2 and carbon-13 make this impossible. And that brings us lastly to how all of this shakes out in the world of climate models. Plotted here is global mean temperature from CRU. The end of the 20th century is warmer than the beginning by just under a degree. But it's hardly a consequence of steady warming. Rather, it results from consecutive decades of warming being incompletely canceled by consecutive decades of cooling. The difference in global temperature results almost entirely from just two intervals. 2 decades during the Depression era, and 2 at the close of the century. Less than 30% of the record. And to be rhetorical, those are the only intervals when temperature has a trend of even the same sign as the trend of CO2. Since 1997, global temperature has experienced no warming. If anything, it's experienced gradual cooling. For the last decade and a half. Global temperature is controlled by the global energy budget. It's measured in units of light bulbs. 1 light bulb is 100 watts. Shortwave energy from the sun, visible radiation arriving at the top of the atmosphere, is some 300 watts per meter squared. That's equivalent to 3 light bulbs illuminating 1 square meter. Of that 300 watts per meter squared, 30% is reflected back to space by cloud, ice, and snow. The rest, the 70% not reflected back to space, is absorbed. Most of it passes directly through the atmosphere, which is transparent to shortwave radiation. It's then absorbed by the Earth's surface, which is thereby warmed. To maintain equilibrium, the Earth's surface emits long-wave energy, infrared radiation, about 400 watts per meter squared, which acts to cool the Earth's surface. Very little of it passes directly through the atmosphere, which is opaque to long-wave radiation. Instead, 95% of that long-wave radiation, some 400 watts per meter squared, is absorbed by the atmosphere, chiefly by water vapor and cloud. They are the primary greenhouse absorbers.
100% increase of
CO2, methane, and all other greenhouse gases account for only 4 watts per meter squared, 1% of the absorption. To maintain equilibrium, the atmosphere also emits long-wave radiation. Almost as much is emitted back down, representing the greenhouse effect. It too warms the Earth's surface, offsetting the energy lost through emission. In this picture, the atmosphere behaves as a blanket. The more atmospheric absorbers of long-wave radiation, the more layers of the blanket, and the greater is warming of the Earth's surface by downwelling long-wave radiation. As CO2 contributes to atmospheric absorption, increasing CO2 adds layers to the blanket. However,
Nearly all of the blanket
comes from water vapor and cloud, and like everything else in this dynamic system, they change. Much of the long-wave energy emitted upward by the Earth's surface, cooling, is offset by long-wave energy emitted back downward by the atmosphere, warming. To maintain equilibrium, the Earth's surface must therefore also transfer heat away mechanically through conduction and convection, vertical air motion that carries heat away from the surface. Associated with cloud and rainfall, it accounts for 30% of overall heat transfer from the Earth's surface.
2 orders of magnitude greater than increased warming by CO2.
Global temperature is the most fundamental climate property, the one on which others rest. It's the cornerstone of climate change. If anything's going to carry the signature of increasing CO2, it will. After all, climate models reproduced its previously observed warming during the 80s and 90s. That led many of us to speculate, well, maybe they are getting it. But reproducing the known change in global temperature is 20/20 hindsight. It's not a strong test of predictive skill. That experiment is called a hindcast. The real test is a forecast, predicting future evolution. Only then can one be confident that models have been tuned to match observed behavior. That's tantamount to a double-blind test, the standard of rigor required in clinical trials of pharmaceuticals. Neither the patient, here the model, nor the clinician, the guy running the model, then knows the outcome. In blue is the forecast evolution of global temperature, averaged over 24 models of the IPCC. The mean evolution is free of decadal variability, which must therefore be incoherent between the models. It follows that on those timescales, the models have no predictive skill. Notice, this is the same timescale responsible for almost all of the 20th century warming. The only feature common to the models, retained in their mean, is a centennial drift. It increases monotonically, becoming 3.5 Kelvin warmer by the end of the 21st century. The increase of global temperature should correspond to increasing CO2. In fact, their correspondence is considerably greater. In green is the forecast evolution of CO2. It too increases, exceeding 800 ppmv by the end of the century. Global temperature doesn't just increase with increasing CO2. It tracks it almost perfectly. In the model world, changes of global temperature and CO2 are isomorphic. They have exactly the same form. Their relationship is so tight, you don't even need a climate model. A fractional increase of CO2 entirely determines the fractional increase of global temperature. The simulated relationship is remarkable. Here's why. Remember the global energy budget? It is what determines global temperature,
Increased CO2 contributes to the energy budget.
but only at the 1% level. The one-to-one correspondence indicates that changes of global temperature remain in equilibrium with changes of CO2, but nothing else. Dominant contributions to the energy budget either do not change, or if they do, they are enslaved to CO2. Those contributions can change only in direct proportion to CO2, which in the model world controls everything. Reflected shortwave energy, which depends on cloud and ice, can't change independently. Mechanical heat transfer from the Earth's surface, which depends on the ocean circulation, can't change independently. And 99% of the long-wave energy absorbed by the atmosphere and re-emitted back downward to warm the Earth's surface, which depends on water vapor and cloud, can't change independently. In the model world, that is, the part that is consistent between all those 24 models, changes in the global energy budget reduced to a highly simplified balance, driven exclusively by CO2. This means that 1% of the global energy budget wags the other 99%. In blue is the observed record of global temperature from the satellite MSU. In green, the observed record of CO2. The long-term evolution of global temperature parallels that of CO2 during the 1980s. It's been scaled to match the trend then, as was obtained by models of the IPCC. With the count of the eruption of Pinatubo in 1992, their correspondence is similar during the 1990s. But after the El Nino of 1997, CO2 continued to increase. Global temperature did not. Their divergence over the last decade and a half is now unequivocal. In the model world, global temperature tracks CO2 almost perfectly. In the real world, it clearly doesn't. Model world, real world. This leads to the following conclusion. In the model world, changes of CO2 and global temperature are closely related. In fact, to within a scale factor, the two are synonymous. They are synonyms for the same thing. In the real world, they're not related. Not quite. The correct conclusion is they're not related directly, as they are under the simplified energy balance that prevails in the model world. Recall, on timescales shorter than a century, changes of CO2 are conservative, controlled by emission from native sources. CO2 then evolves, not like temperature, as it does in the model world, but like the integral of temperature. In dotted blue is the integral of observed temperature. It closely tracks observed CO2, even after the 1990s, when the observed records of CO2 and temperature clearly diverged. If CO2 tracks the integral of temperature, which it clearly does, it cannot track temperature, which it clearly doesn't. In the model world, CO2 and global temperature are related directly. In the real world, they're also related, but differently. The distinctly different relationship between CO2 and global temperature represents a fundamental difference in the global energy balance between its evolution in the model world and the real world. If the global energy balance is wrong, everything else is window dressing. The different relationship between CO2 and global temperature becomes manifest after the 1990s, when their observed records diverged. But once the temperature dependence of CO2 emission is accounted for, namely by native sources, the two observed records are entirely consistent. These features of the observed evolution have the following two-pronged implication. In the real world, global temperature is not controlled exclusively by CO2, not even on long time scales, as it is in the model world. In significant part, however, CO2 is controlled by global temperature. As it is in the proxy record. I'll close with a retrospective of general significance. The science is settled. How often have you heard that? Meet Richard Feynman, described as the greatest mind since Einstein. I had occasion to meet Feynman during my brief time at Caltech, and it was then that he gave a commencement address wherein he spoke on science, pseudoscience, and how not to fool yourself. He noted, one can be easily deceived by deferring to the authority of supposed experts. Feynman developed a paradigm of such behavior, which he characterized as cult science. Feynman also discussed the key to science. Different audience, but the same thing. Here's an excerpt. Now I'm going to describe how we would look for a new physical law. We do so through the following process. First, we guess. The audience breaks up in laughter. No, don't laugh, it's true. Then we perform a calculation to see what are the implications of the guess. And then we compare the result directly with observations. If it disagrees, it's wrong. And that statement is the key to science. It doesn't matter how beautiful your guess is. It doesn't matter who made the guess or what his name is. If it disagrees with observations, it's wrong. That's all there is to it.